Some examples of graphing rational functions from 3.5. Let's say we have this ratio. Now let's examine the vertical asymptote is the vertical line that you never touch. You get infinitely close, but you never get there. The way you find the vertical asymptote is you set the denominator equal to 0 and you solve for x. Why? Because you can't divide by 0. So where the x value that makes the denominator equal 0 is not in the domain of the problem. Now your horizontal asymptotes, what happens to the y value when x gets really, really, really big? We can cross the horizontal asymptote for small values of x, but in the wings of your graph where x is large, the y value will level off at the horizontal asymptote. Y-intercept is where x equals 0. The x-intercepts are where y equals 0. So this is the process of the beginning of the graphing of the function. By the way, if you have a rational function and you want to set the whole thing equal to 0, only the top can make a rational function equal 0. Okay, for our problem here, dividing by 0, you add the 1, divide the 2. You can never touch this. Now the horizontal asymptote is where these x's are infinitely large. So if those x's are infinitely large, the plus 1 and the minus 1 are negligible. The x's will cancel and you'll end up with just 3 halves. Plug in a 0 for the x and you get a plus 1 over minus 1, which gives you minus 1. Set the top equal to 0, solve for x, and you get the x-intercept. All right, let's put all this stuff down. By the way, graphing when you have asymptotes is much easier than without the asymptotes because you know you'll approach the asymptotes, both vertical and horizontal. Remember, you'll never cross the vertical asymptote. In this particular problem, you won't cross the horizontal either, but in the next example, you'll see where sometimes you do. So plotting our x and y intercepts, we see that we pass through the points and we know that we approach the asymptotes. Simple enough? But now we have this whole other domain in which to graph. So we've only graphed from x equals the vertical asymptote into minus infinity. Now we have the whole other half of the graph. So plug in some values for x, calculate the y, and we can plot some points. Then we'll just connect the dots and approach the asymptotes. So plugging in the 2, we got 6 plus 1 over 4 minus 1. Simplify, always reduce your fractions. And you can see this as 2 1/3. That helps us graph that. 2 is pretty simple. Connect the dots and approach the asymptotes. And you're done. Our next example, we have 2 vertical asymptotes. Setting this denominator equal to 0, you see that you have x plus 3x minus 3, so we get plus or minus 3. as our vertical asymptotes. When the x value for this problem goes to infinity, those two infinity squareds cancel, and we get y equals 1. Plug in the 0 for x, you get 0 for y. So let's see what we have so far. Okay, vertical asymptotes are at plus or minus 3. Remember, you never touch vertical asymptotes. They are domain restrictions. And the horizontal y levels off at 1 because the powers of x are the same on the top and the bottom. Plotting the point that we know so far. Now, we don't have any idea what's going to happen in between the asymptotes, so we plug in some values. And we can plug in the plus and the minus at the same time because both of our x's are squared. We'll get the same answer on both sides. Very close to the x-axis, but obviously negative. Plug in the next value, calculate your y value, and you see negative again, a little bit bigger, not quite -1. And now you can see that this is going to look like an upside down parabola or horseshoe in between the asymptotes. Now, what about the outside? We still have all of this domain and all of this. So we're going to plug in some numbers that are outside our vertical asymptotes and see what happens to the y. We'll plot a few points, connect the dots, and approach the asymptotes. Okay, for 4, we get 8/3, which is just 2 and 2/3. So we know where to plot those y values. Both for positive and negative x value, x equals 4, we still get positive y equals 2/3. 2 and 2/3. Yeah, I'm a little bit messy here. One point is really all you need because you know you're going to approach the asymptotes and pass through those points. One of those is a little too high, but you get the point. Plugging in the 5s. (25/16) is 1 and 9/16, so a little bit bigger than 1 1/2. Getting closer to that horizontal asymptote at y equals 1. Now just pass through the points and approach the asymptotes. See how easy asymptotes make your graphing. As long as your graph is as clean as mine, that's all that matters. And now for one that's a little fun. You won't run into this very often, especially in this class. But notice for this problem that if you set the bottom equal to 0, you get a complex number. Complex numbers are not graphed on the real plane, so we get no vertical asymptotes in this problem, which means minus infinity to plus infinity is one continuous graph. Horizontal asymptote, the powers are the same. You get just the coefficients. Remember, if the power is bigger on the bottom, your horizontal asymptote will be 0. Now I know my scale is going to be really big here because my values are going to be very small. And notice that the bottom is always exactly 1 unit bigger than the top. These guys are always positive because x is squared, and then on the bottom you're adding to it. So we know we're always above the x-axis. All of our y values are positive. Also, because the bottom is bigger than the top, for all values of x, we will never get above a 1. So the entire graph is between the x-axis and the horizontal asymptote. Plug in some values. All the x's are squared, so we can do both sides at once. So here we have some y values. We can plot some points, connect the dots, and approach that horizontal asymptote. You see by looking at those y values at 3 and 4, we're getting very close to y equals 1, just a little bit less. So we get a really good idea of what our graph is going to look like. Now one more with no vertical asymptotes. But in this problem, you see that the power on the top is less than the power on the bottom. And because you have infinity times more on the bottom than you have on the top, your y values are going to collapse down to 0. Plug in the 0 for x, you get 0 for y. Let's plot our asymptotes, put some points, connect the dots, and approach the asymptote. This one's a little bit more complicated just with all the fractions, but let's see what happens. Now, plugging in some values for x, be careful with your fractions. This is not symmetric, so we have to do positives and negatives separately. Now, 8/5 is just 1 3/5, bigger than 1 1/2. Now you see by the time we get to 3, our y values, well, actually once we get to the y equals 2 and we start to move out, the y values are getting smaller. They're never going to get to 0, but they'll get closer and closer as x gets larger and larger. We won't go out this far, but we need to see that our y values are getting smaller. So now we're already smaller than 1/2. Okay, these are a little bit difficult to plot, but let's see what happens. Between the 0 and the 1, we're going all the way up from 0 to 2 in the y value. So it's a steep climb, but you see from that point on, as x gets larger, y gets smaller. And we know we'll approach that asymptote. Let's see what happens in between x equals 0 and x equals 1. Be careful with your fractions here. We want to clear that fraction in the denominator, so we'll multiply the top and the bottom by that 4 and simplify what's left. Distribute the 4 and we get 8/5. So we're back at the same y value that we had when x equaled 2. Getting a little closer to 0. This part isn't necessary. You know what's going to happen because you got to connect the dots. But just to check it out here, we get the same y value that we had when x equaled 4. Pretty cool, huh? Now we can really see what's happening with this graph. So connect the dots, approach the asymptote. Now hold on, I'm touching the horizontal asymptote, but that's okay. What happens now when we plug in the negative values of x, we'll get the same y value, just the opposite sign. So we can copy the graph, only flipped upside down. And I'm kind of pretending here, but you get the point.